In 1931, the mathematical world faced a crisis when Kurt Gödel proved that some mathematical truths are fundamentally beyond the reach of any logical proof or mechanical calculation. Before this discovery, David Hilbert proposed that all of mathematics could be reduced to a purely formal system of symbols, where every truth is reachable through a finite process of derivation. Hilbert demanded that any such system must be consistent, meaning it should never be possible to prove a statement and its logical negation simultaneously within the same set of rules. The second requirement was completeness, where every well-formed formula in the language of the system must have a formal proof for either itself or its logical negation.
Finally, the system had to be decidable, implying there exists an effective procedure or algorithm that can determine the truth or falsehood of any assertion in a finite number of steps. These requirements were aimed at foundational systems, like piano arithmetic, which describes the properties of natural numbers using a few simple axioms and the principle of induction. To dismantle this dream, Gödel developed a revolutionary technique called Gödel numbering, which assigns a unique positive integer to every symbol, formula, and proof within a formal system. Each fundamental symbol receives a specific prime number identifier, and complex formulas are encoded by raising a sequence of primes to the power of these unique symbol codes.
Because of the fundamental theorem of arithmetic, every integer has a unique prime factorization, allowing us to perfectly decode any Gödel number back into its original sequence of logical symbols. This arithmetization of syntax means that meta-mathematical statements about logic and proofs can be expressed as ordinary mathematical statements concerning the properties and relationships of large integers. Gödel defined a numerical relationship representing the concept of provability, which is true if one number encodes a valid proof for a specific formula encoded by another number. This provability relation is primitive recursive, meaning that a simple mechanical algorithm can verify whether a sequence of numbers constitutes a valid proof within the axioms of the system. He then introduced a substitution function that takes the Gödel number of a formula and replaces its free variables with the Gödel number of the formula itself. Using these tools, Gödel applied the diagonal lemma to construct a specific mathematical sentence that effectively refers to its own property of being unprovable within the system. Let this sentence be called G. Sentence G asserts that there does not exist a Gödel number which represents a formal proof of sentence G within the current system. To see why this is devastating, we must analyze the consequences of sentence G being either provable or unprovable, based on the core assumption that the formal system is consistent. If sentence G were provable, then there would exist a formal proof for a statement that claims it has no proof, which would create a direct and fatal logical contradiction. Since a consistent system cannot contain contradictions, we are forced to conclude that sentence G cannot be proven using the foundational axioms and the mechanical rules of the system. However, if sentence G is not provable, then the assertion made by the sentence is actually true. We have found a true statement about numbers that is formally unprovable. This gap between truth and provability is the essence of incompleteness, revealing that the reach of mathematical reality extends far beyond the grasp of any fixed formal derivation.
One might wonder if the negation of sentence G could be proven instead, but this would also lead to an immediate inconsistency in the underlying logic of the system. Proving the negation would imply that a proof for G does exist, which we have already established is impossible for any consistent and reliable formal mathematical system. Therefore, in any consistent system strong enough to perform basic arithmetic, there will always be undecidable statements that are neither provable nor refutable by the internal axioms. This result applied directly to major works like the Principia Mathematica by Russell and Whitehead, which had sought to ground all of mathematics in a single unified logic. It showed that no matter how many axioms we add to a system, we can never capture the full complexity of the natural numbers in a single finite framework. Adding the undecidable sentence G as a new axiom simply creates a new, more complex system,
which will then contain its own new version of a Gödel sentence. Incompleteness is not a temporary hurdle that can be overcome with more effort, but a fundamental structural boundary inherent to the nature of symbolic formal reasoning. Gödel's original proof required a condition called omega consistency, which is a stronger requirement than simple consistency, ensuring the system does not prove false existential claims about numbers.
In 1936, the logician Barclay Rosser provided a more general proof that only requires simple consistency to demonstrate the existence of undecidable mathematical sentences. Rosser's construction used a more complex sentence that effectively says, for every proof of me, there is a shorter proof of my logical negation within the system. This improvement solidified the theorem, making it applicable to any consistent formal theory that is capable of describing the standard arithmetic of the natural numbers. The theorem also paved the way for Gödel's second incompleteness theorem, which deals with the ability of a system to prove its own logical consistency.
It proves that any consistent system containing arithmetic cannot prove the specific statement expressing its own consistency using only its own internal tools and rules. This was the final blow to Hilbert's program, as it meant that the absolute certainty of mathematics could not be established from within mathematics itself. We must always step outside a system and use a more powerful set of axioms to verify that the original system is free from internal contradictions. The implications of these theorems reached into the emerging field of computer science, influencing Alan Turing's work on the limits of mechanical computation. Turing's proof of the undecidability of the halting problem is essentially a reformulation of Gödel's incompleteness in the context of algorithms and computer programs. It shows that there is no general algorithm that can predict whether any given program will eventually stop or continue to run forever in an infinite loop. Logic and computation are bound by the same fundamental restrictions, where certain truths remain forever inaccessible to purely systematic or mechanical processes. In set theory, the incompleteness theorem explains why certain foundational questions, like the continuum hypothesis, cannot be resolved using the standard axioms of mathematics. We now know that the existence of an infinity between the integers and the real numbers is independent of the standard Zermelo-Fraenkel axioms. This realization changed the perspective of mathematicians from finding the one true system to exploring a variety of different and equally valid mathematical universes. Some philosophers suggest that incompleteness implies the human mind possesses an intuitive grasp of truth that cannot be replicated by any finite machine or program. While this remains a controversial topic in cognitive science, the theorem provides a rigorous framework for discussing the boundaries between human insight and formal logic. Physically, Gödel's work suggests that a complete theory of everything might be impossible if that theory requires a sufficiently complex mathematical description of the universe. If the universe operates on laws that include basic arithmetic, then there may be physical phenomena that are true but can never be derived from fundamental equations. Today, modern mathematicians use Gödel's insights to navigate the boundaries of what can be known, focusing on the relative strength and consistency of different logical systems. The shattering of the formalist dream did not destroy mathematics, but instead revealed its infinite depth and the inexhaustible nature of mathematical discovery and truth. Kurt Goedel remains one of the most influential figures in intellectual history for revealing the intrinsic and unavoidable boundaries of human reason and formal systems. The first incompleteness theorem stands as a profound reminder that even in the most precise of sciences, there are limits to what can be formally proven by rules.